Hello, this is my video lab report for lab number 2, Projectile Motion. The purpose of this lab was to analyze the motion of an object thrown as a projectile and compare it to two computational models, one with and one without air resistance, or drag. As you'll see in a moment, the experiment was conducted using a paper ball. Regarding the models and fundamental physical principles that were used, this lab applied Newton's second law, or the momentum principle, along with the kinematics associated with projectile motion. For the drag model, I used the given force equation F drag equals negative b times v squared times v hat, which predicts that the drag is always acting opposite to the object's motion. The main results of the lab was that the experimental data closely matched the computational model with drag, showing that the paper ball did experience air resistance. The no-drag model, on the other hand, predicted a much longer flight, which wasn't consistent with the results of my experiment. For the experiment, we recorded the motion of a paper ball being thrown horizontally and measured its position between frames using the program tracker. The system was the paper ball. Its surroundings were Earth, which provided gravity, and air, providing drag. The positive x direction was to the right, and the positive y direction was up, meaning that in both the x and y, the ball moved towards the negative direction. As recorded in Tracker, the initial position was 0.0226 meters in the x and 0.659 in the y. The initial velocity was calculated using some of the initial data points found in Tracker. I got about negative 2.5 meters per second in the x direction and 0 in the y since the throw was level. Here, you can see the experimental setup and how I analyzed the paper ball's motion in Tracker. After setting the axes, calibrating the distance, and marking the ball at each frame, I got the data that you see to the right. For the computational models, I coded the predicted motion in GlowScript using VPython. To do this, I applied the momentum principle, which states that a net force causes a change in the object's momentum with respect to time. I then used kinematics in the form of the velocity and position update formulas inside of a loop so that the object would move in projectile motion. Now remember that I used two models, one with and one without drag. Since the drag force could be tuned with the b value, I was able to set it to 0 for no drag and adjust it to a value that best matched the experimental data, which I found to be 0.00135, as you see in this line of code. To the right are the two inputs, with the top neglecting drag and the bottom including it. Already, you can see that the drag made a difference in the object's flight. Here's the final graph showing all three trajectories. The blue, red, and yellow lines show the observed data, model without drag, and model with drag, respectively. As you can see, the yellow line matches the experimental trajectory much more closely, confirming that air resistance was a significant factor in the paper ball's projectile motion. Now, there were some potential sources of error. One was the limited frame rate of the video, which affected measurements, particularly at the end when the ball hit the ground between two frames, because this caused a little dip that you can see at the bottom of the blue graph here. Moreover, it is possible that my throw was imperfect and created things like spin that were unaccounted for. This lab was also very reliant on estimates, including both my calculated initial velocity that determined the object's motion in both computational models, as well as the b value for drag, which directly changed the trajectory of the model with drag. Regarding terminal velocity, my velocity versus time graphs didn't reach a constant value, but I noticed that my drag model was starting to approach one. Though this experiment did not find a terminal velocity, I could design a similar experiment that would try to create more drag and allow for more time for the object to fall, perhaps by using a parachute and a greater starting height. For the what-if question, if the ball had been thrown straight upward with the same speed, it would take longer to reach the ground. Obviously, it would have to rise up until gravity brought its velocity down to 0, and then it would have to fall back down from this even greater height. For the upward throw, the sum of the times that it takes to reach the maximum height and then reach the ground results in a greater total time than if the ball were just thrown horizontally, which you can see in the equations below. Note that while I only factored in gravity, drag shouldn't affect this relationship since both balls would be slowed down during their flight. To conclude, my lab compared experimental data with two computational models, and of them, the model with drag closely matched, demonstrating that even a small object like a paper ball is affected by air resistance. This highlights the importance of including drag in realistic predictions of motion. Thank you for watching.